All right, we're back. I have approximately 20, 20 something minutes, 20, 25 minutes to crank out some more before the next talk. So let's wrap up some of this stuff so I can submit the midsummer meeting thingy and at least have some stuff accomplished and everything. Yes, yes. When you keep stuff in your head so long, sometimes you just gotta put it to paper, so to speak, or in this case, put it to a digital notebook. All right. So let's share our screen with the class. All right, we're back here. Okay. So, all right, we're at least in the ballpark where we can start telling a story. Let's okay. So we got some more light that. All right, let's go to the kilogram. Let's get a little bit more deep lore there. Okay. A kilogram. All right. All right. Highly polished golf ball sized cylinder of platinum alloy. Yes. Taking place on these commission would become a decimal metric system for mass measurement. A new unit called the grave. Okay. From cradle to grave. All right. All right. All right. All right. Mass towards the end of the 18th century. For some reason we call it the 18th century, but reasons. French King Louis XVI ordered a new system of measure to help prevent fraud. I mean, that sounds like a ongoing thing throughout history. Okay. The commission suggested what later became a decimal based metric system and codified the grave, which is probably not the greatest thing. How many graves you got? Defined as the mass of 1 liter of water at the ice point. The ice point is, I'm going to assume, the freezing point. Ice point of water. Okay. At the point where water would begin to freeze. Okay. Like it might be kind of dense there, although water is fascinating. All right. Continue. The Gray Republic took the new standard, the gram. Okay, yeah. History. Forge, okay. The meter convention. That was the 1870 image, mass and length. Oh, the international prototype kilogram. Okay. So that was in 1879. 1879. That's 1875. Okay, so that's basically that's redundant. Okay, the history. Yeah, okay, yeah. Okay, early inspiration. Which I've waited. Yeah, that's surprisingly accurate. Okay. Okay, we don't need to do the kibble balance. All right, let's just go to the actual way it's based on H bar. Okay, the classical theory, ultraviolet catastrophe, bada boom, bada bang, quantizing makes things fit. Let's see here. Yes, more, Rick, more. Yes, we're going through story time. Oh God, this is. I mean, at least okay. At least the time and length things are at least. I find them more coherent. I'm. Let's just say I'm gathering evidence to rail on the candela and the mole. I'm being unfair, aren't I? All right. Yes. Hey, ain't nothing wrong with some stories and some hot dogs, my friend. All right. Look at the SI kilogram unit body, a single lump of metal cast in the 19th century, be defined in terms of a variant of nature, scaled up or down, conveniently, accurately, and repeatedly. Okay. Their predictions. Okay, I'm using the kibble balance. I'm sorry, I don't want to go into the kibble. Okay, should we go into the kibble? Let's just take a quick look at the kibble. Compares electrical power. Oh, okay, this is important. Brian Kibble, who conceptualized in 1985 the Kibble balance, is an exquisite, accurate weighing machine like any balance. It's designed to equalize one force with another. In this case, the waste of a test mass is exactly offset by a force produced when an electrical current is run through a coil while immersed in the surrounding magnetic field. Okay, so basically they're measuring it. Yes. Okay, the surrounding field is a large permanent magnet system. Movable coil. Once electrified, becomes an electromagnet with a field straight proportional to the amount of current it conducts. When the coil's field interacts with the surrounding magnetic field, an upward force is exerted on the coil. The magnitude of that force is controlled by adjusting the current. Okay. Compares electrical power, magnetical power. Okay. Okay, yeah. Okay, so you're taking the force/weight and you're going to apply the local gravity. Okay, you're going to get an effective force downwards. And if you could calculate that, you're going to have voltage to help balance that out so your scale will be balanced. Okay? Thus, watts of electric power equals watts of mechanical power. All right. And it was really called a watt balance because it took measurements in both current and voltage in the coil, the product of which is expressed in watts. SI unit of power. Okay. To the coil. All right. Yeah. Force is current times a magnetic field strength And then L is the length of the wire of the coil. How is it practical out? Okay. Yeah, okay, your product is... Yeah, you're gonna need a lot of precision. The voltage is increasing, okay. Okay, so that... Okay, where's Planck's constant? H comes to play in the way better current and voltage meter in two different physical constants. Both constants defined in terms of H and the charge of the electron. Those are very small quantities, but both are manifested a measurable macroscopic phenomena. Okay, the von Klingsing constant. Okay, numerical values. The Josephson effect. Constant releasable frequency in a superconducting circuit with measurement uncertainties in a range of 1 part in 10 billion. That ain't too shabby. Where the mass is exactly known in the case of 1 kilogram standard, or it can measure an unknown mass if H is exactly known. The impending redefinition will assign a specific value to H, allowing the kilobalances to measure mass without recourse to the IPK or any physical object. Ooh, it's so shiny. The NIST 4. Okay. Alright. Smaller, deeper, faster. The fully shielded environment. Oh, look at that beautiful, shiny aluminum. Gotta pronounce it the British way. Oh, that thing's big. Yeah, that's a human next to it. Oh, that is a big dude. Let's see. Okay. So let's just quick note. All right. With the advent of the Gibble balance by Brian Kibble at the National Physical Laboratory, not Troy, Tory, in the United Kingdom. Uh, 1975, so we got another date in there. And another source, because we're using it. Okay. No, here, all right. This Kibble, well, it's allowed to quotes weigh objects by the local gravitational effect and offset that by the amount of power in watts required to make the scale balance. Okay, so okay, so the mass grams. All right, so where the mass in grams is equal to the current times the magnetic field strength times the length of wire in the coil. This precision okay. Download gravitational field is adjusted upward. Force on the coil equals the mass. Can we calculate civil reaction? Blah, blah, blah. However, it's practicalized be okay. Due to the necessary accuracy. Okay. This precision was limited to the this precision was limited by the one's knowledge of the magnetic field strength and length of a spring, not string, a spring, a wonderful spring. Everybody loves a spring coil. Well, hashtag not all. Okay, file, save, back. All right. Okay. Let's finish this little part off. All right. Chosen to answer the equation by using Planck's constant. All right, many observers, the connection between mass on a scale of a liter of water, a constant deriving from the earliest days of quantum mechanics, may not be immediately obvious. The scientific context for that connection is suggested by a deep underlying relationship between two of the most celebrated formulations of physics. One is Einstein's E equals mc squared. E is the energy, m is the mass, and c is the speed of light. And we have E equals h nu. Our energy is equal to Planck's constant, the non-reduced type, times the frequency. Okay. Oh, they're using V instead of nu. Okay, yeah. You know, as Planck's constants, Einstein's equations reveal that mass can be understood and even quantified in terms of energy. Planck's equation shows that energy can be calculated in terms of frequency, some entities such as a photon, or alternatively with some mathematical substitutions. A mass times a multiple of h. The multiples must therefore be positive integers, aka the counting numbers. We can count. Such as 1, 2, or 3. The integer aspect is what makes the relationship quantized. Matter releases energy at the straight strikes to as quanta that can be imagined as individual packets of energy. All right. ST and 90, taking two equations yield a counterintuitively but hugely valuable insight. Mass, even though scales of everyday objects, is inherently related to h, which Planck first used to describe the vanishingly small energy content of individual photons emitted by atoms in hot objects. The value of h is about 6 trillionths, blah, 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 of a joule. Of 1 joule second. Pardon. We have to be in the correct dimensions, right? Joules, yes. Unit of energy. Mass with h becomes possible in the 20th century of two separate discoveries. All right. The Josephson constant, all right, so 2 elementary charge divided by h, and the von Klingsing constant, which is h divided by elementary charge squared. Oh, that's why those things pop up when I play on Wolfram Alpha. Cool. I'm so not knowledgeable. All right, the Josephson constant is related to the AC Joseph effect. This occurs when a voltage applies across the superconductor, creates an alternating electric current with a frequency that's proportional to the voltage frequency can be measured more precisely than any other quantity. It's something that's regularly exploited by atomic clocks, which lock onto the microwave or optical frequencies electromagnetic radiation emitted by atoms. All right, so the Josephson constant is an extremely accurate way of measuring voltage. The von Klitzen constant, R sub k, describes a way electrical resistances exist in discrete quantized values instead of continuous ones. In certain terms of physical systems, it is extraordinarily high precision. R sub k is applied to rod as standard electrical resistance. Okay. Mass of a silicon atom by counting the number of alkenes on a 1 kilogram sphere. Yeah. All right. Meteorology, scientific values, Planck's constant basis. Okay. So the exams, a Kibble balance. The process could be reversed by setting an exact value of h. So it's going to be used to measure an exact value of mass. The idea which came to know as electric or electronic kilogram was widely discussed. At least those experiments must produce measurements within a relatively standard uncertainty no more than 50 parts per billion, with at least one of those measurements having an uncertainty of no more than 20 parts per billion. So I must agree with statistical succeed in meeting these requirements. All right, 2017. All right, certainty. National Research had another 2 Kibble balances, 4 measurements from the Avogadro silicon sphere, 1 from blah. The measurement finally produced a final value of h with an uncertainty of 10 parts when SI this. Okay, so basically, that's why, like, when I was going by Thad's old measurements, I'm like, H bar had 12 significant digits. Because post the 2018 release that they probably did whenever, yeah, the 29 redefinition, they just lopped it off at 10. Okay. Okay, so now, all right, we need the Josephson constant, von Klitzen constant. All right. However, physicists, physicists leveraged two constants of nature. The Josephson constant. Hold on. Hold on. No, help. Do I need that? Edit. What did I do? Okay. That's K sub J equals 2 elementary charge divided by H frequency is proportional. Let me just put these in. Josephson constant. Okay, so that relates a voltage to frequency. Relates voltage to frequency, and the Klitzing constant R sub K. It goes this way, which is equal to, that's elementary H divided by elementary charge squared. That describes the way discrete values exist in electrical resistance. There we go. All right. All right, and then we should really get the kilogram, because then we could, okay. So I was like, okay, that's making sense. I'll add some code. All right, so pretty close. So let's save this as again, just because we can. Save as. WSS units project 630 25. All right. That's good. Save to cloud. All right. So I apologize. This is a short one. I got to run to class. I'll just save. All right, cool. Let's close these out. All right, so that's about all we got. Yes, aluminum. It's Kilbass is use electromagnetism and uses electromagnetism and against gravity. That's a good question. All right, I'm gonna have to ponder that later. So other than that, peace out. I'll be back a little bit later, guys. I'll catch you all on the flip side.